In the last video, we learned about different hash functions as well as what are the good properties of the hash function. Once we have computed a hash function, usually we get something called hash code, which is the output of the hash function. In the next step, what we do is we pass this through a reduce function. This could be a standard standalone function, which is an independent function, or you could just have like when you are creating your own data structure, both hash function and reduce step could essentially be a part of the same function. And this reduce step actually allows us to map this hash code, which might be a bit longer than the amount of size which is actually holding our initial hash table, which is like, let's say if our hash table is of size 10, if we have a hash code of like 11775, something like this, out of some object, this index is not there in our initial hash tables because we have confined our hash table to a smaller size like 10 or 100, something like that. So essentially, this reduce step allows us to reduce this hash code into a certain index, which is, it could have like, let's say the most easiest one could be, you could just use hash code mod table size. That's one of the most frequently used reduce functions to allow us to reduce this function into an index, which is, if we do a mod 100 in this case for this particular hash code, we are going to get, our output would essentially be like 75, which is the last two digits. So essentially, we will never get a number that is more than 100. That's what I'm trying to convey. Now, this is not the only reduce function. There could be other reduce functions. Like if you refer to the books, it could be like, it might be using mid squares, or you could use hash code divided by 10 and so on. If you know you have a certain like 8-digit hash code and you know that your table size is like 6 digits, you can always divide it by 10 and like create the final index. But that is essentially the entire sequence of events, which is, once you have the data, you pass it through to the hash function, generate a hash code and reduce it. Now we are going to, like, after all this step, there is still a likelihood that the index you get for two different like data inputs could essentially be equal, which is, in this case, that is called a collision, which is like, let's say if we had like let me do a full formal like sequence of events, which is like, let's say if our hash code was like our data was always strings and our hash code was the ASCII sum of strings. So essentially, like if within this hash function we pass in two strings that looks like this, which is AB and BA, this would yield the total value of 97 plus 98, and the one below would also yield like 98 plus 97. So essentially we would get these values, which is 195 for both of them. And now if we have, like, initially our table size is of like, let's say 10, and if we reduce this as like using a mod 10 function, what we get is 5. So essentially at index 5 in our table, we are storing both AB and BA, which is, we have a collision because AB and BA both belong to that particular index. Now we do what? And that is where we collision resolution strategies come into play. So before we actually go into those, you need to understand these two different metrics. The first one is buckets. So whenever we have a hash table, like the most fundamental structure that is going to hold like all the data is going to be buckets. Like this idea of buckets, which is, you can think of buckets as like locations in the array. Now this array could actually store, like we saw storing this, the array was essentially storing booleans, but it's not necessary that it should store booleans. Like let's say if it is strings, like let's say we had this example of AB and BA, what we can do is, instead of storing this one as Boolean, we can store this as strings. And what we do is like AB generated 5 and BA generated 5. So at index 5 or the fifth bucket, we are essentially storing the string itself, which is AB. Okay. Now when BA comes in, like AB is already stored, what we do is what we are going to see through the collision resolution. But the idea of buckets is that this is the first level of the data structure in the hash table, or like this has to be there in a hash table no matter how you design it, which is the number of buckets is one of the parameters that is used to define a hash function, a hash table, sorry. The second one is load factor, which we had discussed in one of the videos, which is like a metric that tells us how full our hash table is, which is like for this particular example, let's say if the number of buckets was 10 and we had 2 entries, 2 of these buckets were full, or we can just say like 2 values are there in this hash table, that means our our load factor is 2 divided by 10, which is the number of buckets. Now this idea of buckets, this does not mean that one bucket can store one element, because some collision resolution strategies allow you to have flexible bucket sizes, which is one bucket can hold a lot of elements. That's what we are going to see the first collision resolution strategy. But the idea of load factor will always remain the same, which is number of buckets divided by the total number of elements divided by the number of buckets. So which is the total number of elements that are filled divided by the number of buckets. So essentially, like let's say if the bucket allows us to store exactly one element, then this load factor has to be less than 1 always. Like it has to be between 0 to 1. Okay, that's how it is. Like load factor is between 0 to 1. But if a bucket allows you to store more than one element, then the load factor can be much greater than 1. Okay, so how does that work? We are going to see just now, which is there are 2 different types of collision resolution strategies. The first one is using separate chaining. So how does separate chaining work is essentially instead of one bucket storing one element, you could actually store like a linked list or any other collection to store all elements that correspond to that bucket, which is like in this case we had AB and BA. What we did was at the 5th index, like each of these indices are actually pointing to a collection, and you store like AB and BA in like the collection that is pointed to by this bucket, which is like at the 5th index we have like AB, BA stored in a linked list. It could be another set, it could be something else, but like a collection that is storing all the elements. So essentially how it works, like let's say if you get AB, what we do is like if we insert AB, we will get the hash code, or the final value or the index would be essentially 5. We would go to this index 5 and push 5 into push AB into this linked list. If it is not there, then we have BA. We first go into the location 5. We check if there are any other elements. If there are no other elements, we just push BA. But if there are other elements, then you'll have to search through the list. So essentially our data structure might look like this, which is you have these buckets, and at the 5th bucket you have like a linked list that stores ABBA. Now I'm telling you this is a linked list, but it might not be a linked list. It could be any collection. It could be a BST. It could be a graph. It could be anything that you want to design. So, but the general idea is that, which is at a bucket stores a lot of elements. Okay. So this could be fixed and it could be resizable. So what I mean by fixed is like, let's say the problem is like, let's say if we have A, B, B, A, and then C, like any elements that map to like these 5, like maybe like 5, 55, 25, all of these, let's say all of these are adding to this index 5. Now the issue is, like, whenever we want to find an element, the time complexity of finding an element is going to be what? Like earlier it was just O1 because we just were searching at the index 5, but now we have to traverse this entire bucket, the chain inside the bucket. So essentially the find operation or the insert operation is going to be take like O of max size of the bucket, because each of these buckets now have a size, and this max size could get to n. Like let's say if all the numbers are added in, or all the data members are added in one particular bucket, essentially like to search or add new elements into that bucket in the worst case can lead to like O(n) time complexity. So to fix that, we have this other concept, which is the concept of resizability, which is like, let's say if we had 5 buckets here and we had 100 elements. So if we had 100 elements, all of them actually hash to the index 5, we have 100 elements here. Now the time complexity is now of the order of O of 100. Okay. Now how we can fix this is through resizing, which is essentially the, like whenever, like let's say if we take out the load factor of this linked list, okay, so of this hash table, so the load factor will now be equal to the number of elements divided by buckets, which is now 20. So the load factor is 20. So what we do is we cap our load factor, because the insertion and the find operations are directly dependent on the load factor. Okay, so that analysis is given in the book, but essentially what it states is, like let's say if we cap this load factor to, let's say 2, any arbitrary value, like let's say we cap this to 2, what we do is we double the size of the buckets itself, like after we have reached a certain load factor. So essentially, like I'll represent this once again. With a simpler example, because this was a more complicated example. So let's take in just like integers. Okay, so let's say if we had 11, 21, 31, 41, okay, and 51 and 61. Like these are the elements we are trying to insert, and we have a mod 10 function that generates the hash code. So all of these values would land up into, like this is our buckets. The first bucket will have 11, 21, 31, 41, 51, and 61. And let's say if we fix this arbitrary load factor threshold to 0.5, which is whenever our load factor reaches 0.5, we are going to increase the size of our buckets by 2. That's usually the convention. So essentially what we do is, like here we have like 6 elements that are inserted. So load factor is 6 divided by the total number of buckets. So there are 10 buckets that we initially had, because we are using the same convention, which is we are modding it by the number of buckets. So essentially 6 mod 10 is 0.6. So now it has exceeded our preset load factor of 0.5. And when we do that, what we do is we increase the number of buckets to 20, and we also change the reduce function to 20. So now you will actually see that these numbers will land into different positions, which is 11 will land at the 11th bucket now, 31 will land at that 11th bucket, and 61 will also 51 will also land at that bucket, and 21, 41, and 61 will stay at the first bucket. So essentially we are moving the data from one bucket and separating it out into other buckets. So that's the whole purpose of like resizable separate chaining. And that's usually what's followed, which is what we do is whenever we keep track of this load factor, And whenever this load factor exceeds a particular preset threshold, essentially all the values are rehashed. Like that's the concept that's called rehashing. All the values are rehashed into new buckets, and that's the cost we incur. Okay. The other way, which is this was one way of resolving conflicts, which is we were increasing the size of buckets. The other way is called open addressing. That's defined in the book, but how this works is, like, let's say if we had AB, what we would do is we would add AB at the 5th index, and in open addressing what we do is we add another conflict, which is now we have BA. Now BA should be moved to the 5th index, but AB is already there, so you would find the next available slot in this hash table, and if there is like an available spot, you enter it there. So BA would be added at 6. So this is an idea of linear probing. Like let's say after AB and BA, if I had another one, like let's call it like instead of AB and BA, let's say if this was AB and BAC, so I had another permutation like CAB, so, and that had the same like index, which is 5, so it would keep on going and it would add it right here. And let's say if CAB, after CAB we were trying to insert BCA and the table was full, it will go to the first index and wrap around and find a position. So this is an example of linear probing where you find the next available slot. Now in quadratic probing, you do the same thing, but instead of jumping to the next available spot, you jump through quadratic indices, which is like instead of jumping one spot, like after jumping one spot, you may jump to 2 spots and then to 9 spots. Sorry, 1, then 4, then 9, and then 16, which is like it's following the series, which is 1, then 2 square, 3 square, 4 square, and so on. So it will go to those locations. So experimentally, it has been found that quadratic probing works better than linear probing. So that's why it's used. But you can use like these different collision resolution strategies. Now, if you apply like linear probing and quadratic probing, within your methods, you have to deal with all of this, which is like even though you are looking for a particular element, if it is not found, you'll still have to scan through the list and find like if an element exists or is there an empty spot and stuff like that. So doing that, it's like your job as a programmer to handle all of those cases, and it would like apply to all the functions of the ADT itself, like of the operationalization of the ADT, I mean. So that's pretty much it. Those were the collision resolution strategies. I would highly recommend you like read the book and see some examples if you can on these strategies. And in the next video, I'm going to end like the hashing lecture with showing you some examples of C++ on how the unordered sets and maps work behind the scene, and just kind of recap on how this is actually done in C++. Thank you.